Probability and statistics, the binomial distribution. This is a reminder from permutations and combinations. If you're not sure of this, then I would suggest that you have a look at my videos on permutations and combinations first. This comes from the permutation video. What is the probability of obtaining 7 heads and 3 tails when spinning a coin 10 times? Well, the probability works out as the number of favorable outcomes over total number of outcomes. And the number of favorable outcomes for 7 heads and 3 tails is determined by using permutations. Number of arrangements of 7 H's, 3 T's. So we could have 7 first, then the 3 T's. We could have the T's first. We could have an H first, then the T's, then H's again, and so on. So that 10 items, 7 repeats, 3 repeats. So we will have 10 factorial over 7 factorial, 3 factorial, giving us 120. Now, that is the number of favorable outcomes. The total number of outcomes, well, there are 2 possible options for each of these, so 2 to the 10, giving you 1024. So the probability of obtaining these 7 heads and 3 tails is the number of favorable outcomes over the total number of outcomes, giving you 0,117. So, on to the binomial distribution. It's all about 2 results. All about 2 results. That's where the bi comes from, bi for 2. Let's have a look at an example. We toss a coin 3 times. What's the chance of getting 2 heads? Well, let's look at the sample space. There's the sample space for tossing a coin 3 times. There are all the possible options that we can have. Now, to find the chance of getting 2 heads, there are 8 possible outcomes. They're the number of outcomes which have 2 heads. So therefore, our probability is just going to be straight 3 favorables, so the probability is 3 over 8. Now that was also by probability formula, but we're actually going to use more the principles of permutations as well. So, number of favorable outcomes. We know there are 3, so in how many ways can they be arranged? How many arrangements can be made with 2 heads and 1 tail? Well, that's one of those repeat questions. Arranging 3, so it's 3 factorial, 2 repeats, so we're dividing by 2 factorial. That we're going to put over 2 cubed, because that's how many there are. There are 3 multiplying together, giving us 3/8. Now notice in this case, we didn't go to the whole sample space. We don't need to. Same answer. So, if we toss a coin 8 times, there's the total number. That's the whole sample space there, just abbreviated. What's the probability of obtaining 2 heads tossing a coin 8 times? Well, there we are. Head, head, tail, 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 tail. But then we've got to say, well, there are a number of arrangements of those. There are 8 factorial over 2 factorial, 6 factorial. So this number of these satisfy this requirement. So therefore, the probability of 2 heads is that number of arrangements divided by total number. Now if we have a look at the whole distribution, 0 heads through to 8 heads, there's our 2 heads. You'll notice that 2 heads has the same probability as 6 heads. 0 heads has the same probability as 8 heads. So there's a symmetry about it. And that gives us our binomial distribution. It is in fact in the shape of the normal distribution. So when do we use binomial? First of all, if there are 2 possible outcomes, success or failure, head or not head. The probability of success is the same in each event, or in other words, the events are independent, meaning that success in one event does not influence the probability of success in another. If you spin a coin, that does not affect what happens in the next spin. So here's an example. What's the probability that a sum of at least 10 is obtained in 3 of 5 throws of a pair of dice? Well, 2 possible outcomes, greater than or equal to 10 or less than or equal to 10. There's success, there's failure. Now, if we had to count them, there's the number giving greater than or equal to 10, which means the probability of greater than or equal to 10 is 6 over 36. Now, that we need to know in binomial theorem. We need to know the probability of success and the probability of failure. So we have just worked out probability of success. The probability of failure, seeing there are only 2 possible outcomes, is pretty easy. We'll just say 1 minus 1/6. So the probability of failure is 5/6. Now, for example, if we had to calculate the probability of that, it would be 1/6, 1/6, 1/6, 1/6, 1/6, 5/6, 5/6. Problem being, though, that that's only one of the outcomes in throwing these dice. There's another one. We don't have to get 3 greater than 10 on the first 3. We could have greater twice and then less than, and then greater and then less than. There's another one. So we need to say, all right, so there's the probability of that one. Now, how many of these are there? And that is going to be worked out as the permutation. 5 factorial over 3 factorial, 2 factorial. 5 for the total number of objects, 3 and 2 for the repeats. So in fact, the probability of 10 or more is the probability of that one, there it is there, there it is there, multiplied by the number like that one, which is that. So there it is there. That giving me 0,32. So we have a formula for the binomial probability distribution. And it comes from here. Total number of outcomes times the probability of one of the outcomes. There we are. Probability of success to the x, because you have x out of n, times probability of failure to the n minus x. And there's the number of arrangements we can have. We're arranging x and then n minus x of n items. It's only those 2 because it's binomial. There are only 2 options. And we can see that hopefully as a combination. It's often written as a combination, especially the brackets with 2 numbers above one above the other. So probability of obtaining 5 heads in a spin of a coin. So first we need to know the probability of one of the options, and then of course how many options. So there's the probability of one of the options, half to the 5, heads 5, 1 minus half, the 7 minus 5, because it's 2 tails. And there's the number of possible ways this can happen. Probability of obtaining 2 5s in 5 throws of a die. Same thing, we can work out the probability of it happening in 1, which is 1/6 squared for the 2 5s, and then 1 minus 1/6 to the 3 for the 3 non-5s, and we multiply the number of ways that we could have this 5, 5, not arranged. The probability of Gemma winning any tennis match is 0,3. What is the probability that she'll win at least one of the next 3 matches she plays? Now, as soon as you see this at least one, that means you need to calculate 1, 2, or 3, or there's another way around. Whenever dealing with at least one, it's better to deal with it as 1 minus probability of none. Because the binomial theorem, at least one is the success, the failure is none. So there we are. 3C naught, 0,3 to the 0, because that means that's the probability of winning, and winning none, and 1 minus 0,3 to the 3. 0 factorial equals 1. So 0,657, that's quite interesting. So if she has a probability of 0,3 of winning any match, then the probability of her winning at least one in the next 3 is 0,657. There's the other notation for using the combination. And while we use that mainly, that is often used in the binomial theorem formula. A student is answering a 10-question multiple choice test in which there are 4 answer options, of which one is correct for each question. He has done no preparation, meaning that he will have to guess each answer. That's why it's a he, because if it was a girl, she would have prepared. What is the probability that he passes if the pass mark is 50%? Well, lots of people feel, well, I have a good chance if I guess. So 5, up to 5 correct. So we'd have to work it out as none correct, 1 correct, 2 correct, 3 correct, up to 5 correct. Or 1 minus probability of, so there we are. Probability of 5 correct, probability of 6, all the way up to probability of 10 correct. We'd have to work it that way. Or we could do 1 minus probability of less than 5 correct. Slightly shorter, 1 calculation less. These are all binomial theorem. The probability of success is 1/4 because it's 4 answer options, and obviously the probability of failure is 3/4. So there we have it. Probability of 0 is 10 0, 1/4 to the 0, 3/4 to the 10. Then we'll have 10 1 and 1 9, 10 2 2 8, 10 3 3 7, 10 4 4 6. That's actually quite amazing if you think about it. So if you are doing a 10-question multiple choice test in which you're guessing, you have very little chance of passing that test. So, research establishes that in a university with 15,600 students, 1716 are left-handed. Found correct to 2 decimal places the probability that a student selected at random is left-handed. Well, it's 1716 out of that. So therefore it's going to have the favorable outcome divided by the total is 0,11. Now, B. In a group of 8 selected random, fewer than 2 students will be left-handed. So in other words, we want if none were left-handed, 1 was left-handed. So it's mutually exclusive. We'll have to work out probability of none, which means right, going all the way through for 8 occasions, or left and then right through for another 7 with the different arrangements. So, probability of less than 2 left-handed, probability of 0 plus probability of 1. 8, 0, 8 selected random, none. 0,11, that's the probability of being left-handed, and 1 minus 0,11 to the 8. Then here, probability of 1 being left-handed by binomial theorem. So the probability is 0.78 that fewer than 2 will be left-handed. C. That there will be at least 2 people in the group who are left-handed. Now that could be a complex question, because if it's at least 2, that means 2 or 3 or 4 up to 8 could be left-handed. Or, think about it, we can do it an easier way. Have a look at B. We've just worked out fewer than 2. Now at least 2 is the complementary event. So therefore all we have to do is 1 minus the previous answer. And therefore the probability is 0.22 that there will be at least 2 who are left-handed. Now here's an interesting one. A quality controller in a factory producing mini clamps tests the clamps by drawing 1,000 at random for testing through each month. The latest record shows that 23 faulty clamps were found in the previous test. That means over the previous month, 23 were found faulty. These clamps are sold in packs of 4, and the quality controller knows by experience that about 60% of the packs with faults are returned to the factory. Based on the previous monthly test, what is the probability that a clamp chosen at random will be faulty? Well, 23 were faulty, drawing 1,000. So pretty straightforward. 23 over 1,000, 0,023. B. If a shopping chain orders 10,000 packs of clamp, how many returns should be expected from this order? Well, let's have a look at this. First of all, we have to work out the probability of 1 pack of 4 having a faulty clamp. From there, we can work out by multiplying how many of the 10,000 are likely to have a faulty clamp by multiplying by the probability of 1 being faulty. And then we'll have to take 60%. Right, so probability of at least 1 faulty clamp in a packet means 1 minus probability of no faulty clamps in a packet. Which means 1 minus 4C0, because it's 0 out of 4 faulty, 0,023 to the 0, because that is the number probability of faulty, times 1 minus 0,023 to the 4. Now remember, we're working out the probability of at least one faulty clamp in one packet, which means the probability of having a faulty clamp in a packet is 0.0889. Now, if there are 10,000 packs ordered, we're going to have to multiply that probability of 1 being faulty by the number of packs, and then don't forget the 60%, because only 60% are returned, giving us 533, which means that the quality controller, the factory, should expect 533 returns from those 10,000 packs ordered.